This is the hidden cost inside DI-constrained SBQ grades that no one is talking about. Here's a typical scenario that we see. Your steel meets spec, your DI passes, but you're still overspending on alloy by about $5 per ton, and your quality system will never flag it. Most process engineers don't realize that the solution is simple. This is what's happening metallurgically. The ASTM A255 DI calculation is multiplicative across 8 element factors: carbon, manganese, chromium, molybdenum, vanadium, nickel, silicon, and copper. Carbon alone uses 6 separate polynomial segments. What that means in practice is this. There aren't a few chemistries that hit your DI target. There are millions of chemistry combinations capable of producing the same DI value. But your level 2 system isn't searching that chemistry space. It's aiming at a predefined chemistry target, usually somewhere near the center of the DI band. From a production standpoint, that makes sense. The heat lands in spec, operators trust it, production keeps moving. But that target chemistry isn't the lowest cost chemistry capable of meeting DI. So the heat ships. The steel meets every specification, and the mill quietly spends a lot more alloy than the heat actually required. That difference has a name: the alloy gap. And at one North American SBQ producer, it averaged about $5 per ton across heats that passed every spec. That may seem like a small amount, but when you scale that across your DI-graded volume and across multiple sites, the savings are significant. What steel mills are starting to do now is optimize DI chemistry instead of just aiming at it. Software like Fero Labs evaluates the entire chemistry solution space and identifies the lowest cost alloy combination that still satisfies the DI requirement, all within the trim window, heat by heat, recalculating with each ladle sample. And it works alongside your existing level 2 system, not instead of it. That means there's no workflow changes for operators, so efficiency improvement comes without any production friction. If DI optimization is interesting to you, we break down the math, the solution, and a real production heat example in the full article linked in the description. And make sure you subscribe to our channel for more content like this.